The discourse that we are engaged in is whether the Earth is special or is it commonplace. And this we can answer from multiple directions. Good morning, everyone. Thanks for being here. I'm going to let this laptop warm up for a second. As John mentioned, the discourse that we are engaged in is whether the Earth is special or is it commonplace. And this we can answer from multiple directions. By the way, I want to send a distress signal. I think my laptop died, so we'll go to plan B, which is fine. I can talk about it without the slides. So basically, the story starts, the way I want to tell you the story is just about 3 decades ago, 1995, for the first time, a planet was discovered orbiting another star. This time, not our sun, but another star. And the star was 51 Pegasi, and the planet was observed indirectly. It was not actually observed. What happens is that when a planet orbits a star, the planet basically drags the star around a little bit. And this is essentially a recoil phenomenon. So the planet is maybe 10 billion times, maybe 100 billion times less bright than the star. So you're barely seeing the star. You're not going to see the planet. But you will see slight red shifts and blue shifts of the star as it sometimes comes towards you and sometimes goes away from you. And that slight amount of motion, that's about on the scale of 100 miles an hour. Basically, just imagine, I asked you if a car was coming towards you and then came to a full stop. And meanwhile, you're looking at its headlight. Do you see a color change when it stopped compared to when it was going? You won't. It's a very small effect. You have to go to a good fraction of the speed of light to see it. But that wasn't. But the sensitivity of these instruments is high enough to be able to do it. By the way, the laptop did wake up finally, so we'll be there. So since then, that was 1995. This is 2024. This is now 30 years, just about. Another year, and it'll be 3 decades. And in 3 decades, we've seen 5,000 exoplanets. Actually, 5,500 at the latest count. And so we now have an idea about essentially the census of the planets, not just from the 9 planets of our solar system, but this is the 51 Pegasi, and that's the Doppler shift. Not just from that standpoint, but from the standpoint of now an ensemble of 5,500 stars and planets. And we can ask the question, okay, in terms of Earth's suitability for life, is the Earth typical or is it atypical? And the kind of thinking that says that Earth is not special is essentially saying that to have a planet is to have a habitable planet. In other words, the requirements for habitability are so loose. Now, if this thing would only advance, I'd be very pleased. Okay, that'd be great. That the requirements are so loose that just once you get the planet to form, it'll be habitable. And this whole notion of the habitability and the requirements for habitability then become the big question. What makes a habitable planet? Is any planet a habitable planet, or do you need certain requirements? Really, it is not unknown, and it is widely acknowledged that no, there are requirements. The first one is you need a terrestrial planet. A planet that is terrestrial. Terra means earth, it means dirt. Dirt is very special in the universe. It is the product of stellar fusion and stellar explosions, many generations as the heavier elements are formed. Much of the universe is hydrogen and helium. Dirt is very precious. Next time you walk and you see some dirt, appreciate it. The other thing is it needs to support complex carbon and water-based life. Carbon holds a very special place in its ability to form macromolecules that are the language, essentially, or the vehicles of life's chemistry. You can't do this with silicon. The periodic table only has so many slots, and that particular column is very special, and that particular row is very special, and you only have carbon there. And so anywhere in the universe, you want to produce very complex macromolecules that do all the esoteric things that life requires, you need carbon. And then you need the carbon chemistry to be active, and water facilitates that. And then you need the water to be liquid so that the carbon chemistry could go. So that is what I mean by it needs to support carbon and water-based life. To do that, you have to be in the circumstellar habitable zone. Now, I haven't mentioned what that is yet. We'll go over that in a bit of detail. But basically, the point is, not everywhere is good enough around a star. You have to be at the right radius around the star. And guess what? Even the star has to be in the right radius within the galaxy. And so you have all these requirements, and we're going to examine each of these, and then we're going to see a ton more. So back to the planets. So I mentioned the 5,000 exoplanets that have been discovered. This is a NASA poster that just kind of broadly categorizes the kind of planets that have been seen. Some 30% of the stars are gas giants. These are like Jupiter and Saturn. If I were to drop you off and say goodbye, on a gas giant, you would not settle anywhere. You would just keep going down through thousands of miles of gas as the pressure increases to a point that you get to a state of metallic hydrogen. You're not going to survive that. So the other group is like Neptune and Uranus, the Neptune-like, another third-ish, that are also, these are ice giants, these are not habitable planets. Then what's left is super-Earths that are terrestrial. They start out terrestrial and mini-Neptunes. But these are very massive, and their massiveness tends to kind of make uniform their surface structure, which may in fact be not conducive to life. So in the end, you have just a sliver at 4% that is terrestrial planet like the Earth. Now, suppose you do have a terrestrial planet. Where do you put that planet? This plot is a sort of a pretty version of a very famous plot by Jim Casting from, I think in the 90s, and in which what it shows is for every type of star, and that's on the left side, you see these, the very bright blue, what astronomers call blue, that doesn't look blue, but it's blue relative to the red, and all the way down to the red star. The redder star is a smaller, cooler star. The bright blue stars are very active, very young, very, very energetic stars, and they're short-lived. The sun holds what looks like an average place. And that's a little deceptive to say an average place because it turns out that the average place is not very occupied. So we'll come back to that in a minute. But let's just take that row. That is our sun. From the left, we see some planets. We see Mercury, Venus. Then we see Earth in blue, inside of that blue strip. That blue strip represents where you could expect to have liquid water. That is sort of the crudest, most simple way to describe the habitable zone. Okay, the circumstellar, around the star, habitable zone. After that, we've got Mars. Mars doesn't quite make it. It's outside. And then we've got Jupiter and the rest of the planets. Now, you notice that as the star gets cooler, the habitable zone has to come closer. Why? Because it's cooler, you have to get closer to the fire to warm up, basically. But this diagram is only describing things from a very simple point of view, from a standpoint of view of blackbody radiation. If we then include the greenhouse effect and an atmosphere, things get tighter still. This is a paper by Francois Forget from just a few years ago, and it shows how the atmospheric dynamics actually make things even harder. Because what happens is if you, for example, take the Earth and just go a little bit closer, maybe as much as a few percent of the distance it has from the sun, just go a little closer, what happens? Well, that extra heat basically boils off the oceans. It first starts just evaporating at a higher rate. That higher evaporation causes the most important greenhouse gas, and that is water. The most important greenhouse gas goes up into the atmosphere, in which the greenhouse effect then increases the temperature of the Earth, which, guess what? What does that do? Well, that means more evaporation. And that's a vicious cycle. More evaporation, more heat, more evaporation, more heat. And all this water is in the atmosphere. Well, that's not where the story ends. The UV from the star, then the ultraviolet radiation dissociates water and hydrogen. The hydrogen goes way to the top of the atmosphere, and it's blown away with the solar wind. The planet is desiccated and dead, okay? And so the inner edge of the habitable zone, even in our case, just a little further, and it won't be right. On the other side, you get the opposite problem. As you go farther away, now you're cooler, a lot more chance of snow, and snow is white. And so what that happens, the albedo goes up. Albedo is the fraction of light that's reflected and doesn't heat the Earth. So if you have the whole snow, the ground covered with more snow, it's going to be colder. If it's colder, then it's going to snow more, which means it gets colder still, and you get what is called a snowball Earth. And so on both edges, you have more tightening of the habitable zone for these reasons. Now, we said all this in the context of ourselves and our star. What about other stars? There are other stars. This is one way of representing them in this plot. We have the standard color luminosity plot. The vertical axis is the luminosity of the star, and the horizontal axis is the sort of the representative color of the star. It's basically how reddish or bluish it is. Most of the stars in the sky, about 80%, are down here at the red end, okay? The blue end, which is at the top, those are too short-lived and there's too much variation in their intensity to make them habitable. So in the middle, there's only about actually about 6 to 7% that are G stars like our sun. And our sun is is relatively massive, very, very stable, really benevolent star as far as these things go. But the other thing is that if you look at the sky and look for all the G stars, half of them are in binaries. And a binary is basically, there are two stars that are orbiting each other. And now if you're a measly little planet trying to make it in this world, those two stars, their tug of war is going to rip you apart. And so a lot of times those planets that are in binary systems will risk being ejected actually out of the system. So that really of that 7%, only half really are reliable. So about in all, 3.5, 4% of the stars are going to be amenable to a true sun-like condition. But you may say, well, okay, fine. What about all that 80% that is the red dwarf? What about those? Well, those, by the time you get that close to a star, it turns out a new effect takes place. The gravitational pull of the star on the planet takes the spherical planet and turns it into a slight jelly bean. Then the gravitational force on the near side and the far side are different. And the planet, which is spinning, starts spinning slower. It turns out it works out that when that happens, it will slow down the spin. That will continue to slow down the spin until the spin rate of the planet matches its orbital period. At that moment, the planet is what is called tidally locked to the star. One side is always facing the star and can't move away. Okay, our moon is tidally locked to the Earth. That's why we always see the same side of the moon. It goes with the 6th power of the distance. So it's very strong effect. So with these M dwarfs, these red stars that are the most abundant, where you would be for the habitable zone is where you would actually have tidal locking. In which case, one side, the heat is constant and boils off all the liquid water, and it all snows on the backside. You may have a terminator, the sunset-sunrise terminator, where there may be some liquid water, but that is nothing resembling a habitable Earth. There are newer work, this is only a few months old, by Hall et al., that says that actually that habitable zone has another constraint, and it's photosynthesis. And I keep saying photovoltaic, so if I do, please forgive me right now. There is, from a standpoint of how much energy you need to be receiving, there is a zone in which optimally a potential photosynthesizing process needs to have you be. But at the same time, you want to have liquid water now the intersection of the two mean that if you want both liquid water and photosynthesis, that you get that dark green little sliver. And that is now called the photosynthetic habitable zone, and it's a more constrained habitable zone. So now what we're doing is going over, talking about the constraints on life, one after another, okay? And that's, the next constraint is plate tectonics. Now, plate tectonics give us, come along with earthquakes and things we don't like, but plate tectonics also circulate the minerals on the Earth for life. They regulate carbon dioxide, which is a greenhouse gas, and help regulate the climate. The plate tectonics ends up being very important for life. But it turns out theoretical work has shown that plate tectonics appears to be hard to produce. So in the models where they try to reproduce sort of a formation of a planet, they find that this business of subduction, where one layer goes under another, doesn't seem to quite happen, and that the densities aren't right. It's almost, they said, like you take an inner tube and you're trying to force it under the water, and just the moment you let go, thing pops up. So these subducted layers don't stay down in the models. It is not quite clear what it takes to make this happen. Obviously, it happened here, but doesn't seem to be coming very easily. So that's plate tectonics. Another one, interestingly, is our moon. We have an anomalously large moon, and it serves to stabilize the axial tilt of the Earth. Well, the axial tilt of the Earth, what is that? Well, the Earth is spinning, but it's not spinning relative to its the plane in which it's orbiting around the sun. It's not spinning kind of perpendicularly. It's got kind of an angle. And at that angle, that's why half the year, a quarter of the year it's summer, and a quarter of the year it's winter. We get the seasons because of that tilt, because the northern hemisphere gets a time where it is seeing sun directly. Now, the axial tilt exists on other planets. The problem is it exists too much. On Mars, the axial tilt varies by as much as 80 degrees. And so it just wreaks havoc on temperatures because there's no stable axial tilt. The moon stabilizes it. It stays within a few degrees of 23-ish degrees. And so that the moon serves the Earth in protecting the climate of the Earth. Similarly, we have the outer planets, interestingly, serving the Earth. Our solar system is like a clockwork of very well-behaved, circularly orbiting planets around the common star. It is not always so, and in fact, as we will see, this is very unusual to have this situation. An orbit doesn't have to be circular. In fact, the normal orbit will be some degree of elliptical. It will have, and that ellipticalness, there's a mathematical word that some of you in geometry might have heard. It's called eccentricity. So the eccentricity, when it's 1, that means you're so elliptical, you look like a line. And when it's 0, it means you're a perfect circle, okay? And so all of our planets have an eccentricity down around 0.05-ish, very circular, very circular. What does this mean? This means, think of a planet like Jupiter, hundreds of times the mass of the Earth. Heavy planet that absorbs to itself all the junk of the solar system, the comets and the asteroids, the things whose impact on this Earth would be devastating. And it absorbs it to itself, and it's like a cosmic vacuum cleaner, just cleaning everything up, while politely staying at its 5 astronomical unit radius orbit, not moving near us. So it's out there protecting without coming around to be dangerous. This actually turns out to be unusual. The other thing is, of course, you need oxygen. But what if you had only oxygen? A spark and the planet goes up, So we have oxygen, nitrogen, 4 parts nitrogen, and that has many benefits, but it certainly has that benefit. We talked about water. You need water for the carbon chemistry to work. But what if you had just massive amounts of water? What if it was just oceans? There was no hills, no mountains, nothing. Well, at that point, you have a problem because you need the radiation from the sun. You need the solar radiation. You need the light and the water. And you need materials to work with. And in the areas where land comes to near water and the shallow water, you get all these conditions. You get light, you get water, you get heat, and you get the minerals. And so it's very conducive to life to have those conditions. And so you need to have the right amount of water, not every amount of water. The next thing you need is a protective shield, because the universe is a dangerous place. There are cosmic rays that will radiate you to smithereens over a long period of time. On this one, rather than talk myself too much, let me show you a absolutely remarkable NASA video. I just love this thing. It's going to watch 3 minutes of it.
What safeguards our solar system is our star. The sun provides a shield stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays. But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper atmosphere, hydrogen, oxygen, and the molecule they form, water. What's left is a witch's brew of noxious chemicals, including thick, sulfurous clouds. How has Earth avoided the grim fate of Venus? We can see the answer as the solar storm approaches Earth. Our planet has a protective shield all its own, a powerful magnetic field generated deep within its core. In fact, that's just our first line of defense. Much of the solar energy that gets through is reflected back to space by clouds, ice, and snow. The energy that Earth absorbs is just enough to power a remarkable planetary engine, the climate. It's set in motion by the unevenness of solar heating, due in part to the cycles of day and night and the seasons that cause warm, tropical winds to blow toward the poles and cold polar air toward the equator. Wind currents drive surface ocean currents. This computer simulation shows the Gulf Stream winding its way along the coast of North America. This great ocean river carries enough heat energy to power the industrial world 100 times over.
Well, it's a great video, but we have to move on. Yeah, this is really remarkable to see how much intricate work goes into even making our climate. So we see that the Earth itself has a lot of very well fine-tuned conditions all together to make it a habitable planet. But in fact, if we now take a step backwards, where we are placed within the galaxy also becomes important. It turns out if you look at a picture of the galaxy, our Milky Way galaxy, it is already a special kind of galaxy. It is among the more massive galaxies. It's well developed. It's got these spiral arms. But not everywhere in the Milky Way is habitable. If you are, let's say that you want to think that maybe you want to be downtown at where all the excitement is. Well, where all the excitement is a supermassive black hole, and you would not survive approaching it. The other thing is that as the density of the stars increases, the probability for stellar explosions, and particularly supernovae, increases. And as that happens, a supernova event essentially strips out life within light years around it. And so if these things are popping up frequently around you, there's no chance life can have any chance near you. So you want to stay away from the center, but now let's say you just want to stay way out in the country. Well, it turns out that the heavy element abundance outside in the outer radii is too low, and you don't get terrestrial planets there. So you can't be too close, you can't be too far, and that was where Guillermo Gonzalez, actually, who's speaking next with Jay Richards, they discovered the existence of this galactic habitable zone. And in the galactic habitable zone, you still have to be careful because you can't be in the spiral arms for essentially the same reasons. The spiral arms are where there are higher densities of stars, and therefore a lot of potential for these transition radiation events, these events that can destroy you. And so you kind of stay outside the spiral arms in a particular radius, which is called the co-rotation radius, where you're going around the center of the galaxy at the same rate as the spiral arms so they don't swoop over you too fast. So that too has to be special. So now, at this point, what we've done is talk about what are the requirements, what I would call in a sort of a theoretical sense mostly. We talked about on first principles, what would we expect? Now we'll take a brief look also at the experimental side of this. Now we mentioned the radial velocity technique. That was the first one that I mentioned where you look at the Doppler shift. Another one that's very simple for detecting exoplanets is the transit technique. In which case, but we have to get lucky. In other words, if you have a star and a planet, and let's say you're where you are right now, you're looking at my hand, the star. If a planet is orbiting like this around it, it could, you're not going to see anything. So you have to be kind of like fortunate enough to be in that plane or close to that plane. And then you see the transit of the planet in front of the star. And what do you see? You see about 1% worth of drop in the brightness of the star. So you have to have what is called very precise photometry. And you want to measure that 1% to about 1%. So now you're getting really, really special, And so this has been done. This is now for about the last 15, 20 years that has been possible. And I'll mention some of the results. This is another technique that is becoming online rapidly, and it's going to become a very important technique, which is coronography or occultation, in which you essentially, if you thought about it, you go, well, what's the big deal? I'll just take a picture of the solar system, the star system. I'll look for little dots. They'll be the planets, and we're done. Well, the problem is that the wave nature of light will fight you. From any reasonable sized telescope, the blob of light that represents the star, the star is so big that it just swallows up by a factor of millions any light from the planet. But there are now very fancy things we can do. And this is a project I've been involved with for 10 years at Jet Propulsion Lab. And now Guillermo Gonzalez and I are both working on it. We're actually doing the testing as you can see, it looks pretty much done now. This is a coronagraph instrument. It is designed to block out the starlight by manipulating the incoming field from the star, or the light wave that's coming from the star, so you can see the planet. And a more sort of a cruder version of it works on a ground telescope, on the Keck telescope. And those planets that you see are actually very far away relative to our solar system's planets. And they're self-luminous. But these, you can see this is like 12 years of photos putting on top of each other makes a movie. You can clearly see the planetary system in a beautiful way. So this is going to go online in about a year, a couple of years. All right. So going back to the transit search, the Kepler mission, which is now retired, basically did this. You can see one of its data products over there. The measurement, you can see the dip. And from that, we learned something. We learned that only a few % of the stars have Earth-like planets. That result that we saw early came from the transit search, that we said that only 4% are terrestrial. From the radial velocity, we learned a lot of things from the radial velocity detection. This plot shows in the vertical axis the eccentricity or ellipticalness of the orbits of the planets that we're seeing. On the horizontal axis is essentially the orbital period, or you can think of it as orbital radius. And what we said we liked from Jupiter was that it was massive, it was far, and it was circular. If it's circular, you want it right at the bottom of that curve. Those are the good guys. All the ones that are higher up, those are not circular orbits. They're going to come in close and smash against the planets that are inside. Okay, but you can see that there is a whole bunch, but they are what they call hot Jupiters. That orbit, it's hard to read, but it's about 1 day orbit. That planet is whipping around the star at once a day, And so and in fact, as we will find out, in fact, I'm going to jump to it now. This paper says that, by the way, that planet, by the time it came there to become a hot Jupiter, it slaughtered all the other planets. That they start in these large elliptical orbits, and their orbits essentially get circularized. On their way to getting circularized and so-called well-behaved, they destroyed everything else. And that's why the authors say, when we find these, we don't find anything else. That's essentially all there is, because they knocked everything out. So hot Jupiters are not your friends. Another paper that came, this is a result of transit studies, makes a beautiful plot. This plot is a little bit hard maybe to read from here, but basically this is a logarithmic scale of radius. And there are circles drawn, they're kind of faint. There is a circle drawn for Mercury. You can see the word Mercury at the bottom, and you can you follow it, and you can see that circle. Now, what's interesting about that? That is the orbit of Mercury. And almost all the exoplanets that the transit technique saw are inside of the orbit of Mercury. They're all closer than Mercury. That other yellow circle is 10 times the solar radius. I mean, these things are just blistering hot. Where Earth is, almost none of the planetary systems are there. And the authors of this paper say, when viewed in this context, the solar system is unusual. The raw contrast to our own solar system is striking. It's that when we're observing other planets, we see that, wow, things are very different than what we have. All right, I'm going to conclude this talk by just a discussion of then what do we expect with numbers. Now, back when the Search for Extraterrestrial Intelligence, or SETI program, was new, around 1961, they had a meeting in which a noted astronomer, Frank Drake, presented a paper in which he tried to just say, look, this thing's complicated, but let's just kind of take a moment and do a very quick math. And we can ask, what is the rate at which stars form in this galaxy? And then of those, at what rate do we expect planets to form? What rate do you think on those planets, what fraction of those planets would be good enough for life? Of those, what fraction would actually form life? Of those, what fraction that life would become intelligent life? And of those, what fraction would be able to send radio signals? And of those, what fraction would survive long enough before they killed each other off in a war to send us those radio signals? And he came up with an estimate of, in our Milky Way galaxy, maybe up to 10,000 advanced civilizations should be sending us signals. So, heartened by these numbers, they started searching. They're still searching 60 years later, and no signals. The reason by now is probably obvious. Drake's equation was a little too optimistic. For 1961, it was brilliant. But by 2024, it's not really appropriate. Because we now know these conditions. Both observationally and theoretically, we have many, many more requirements. And different lists, different astrophysicists will have different lists for you, but a typical list might have 20 items in it. And then you have to ask, well, you want all these conditions simultaneously true. Now, if you want multiple things that are independent, this is just a theorem of statistics. If you want independent things to simultaneously be true, you have to multiply the probabilities. Now, the thing is, these are not all independent. So if you get one, you might get some of the other. So you can't quite do that. But many of these are pretty independent. And so what you can do is you just say, well, okay, I got 20 things. Let's say 5 of these are just totally correlated. I'll give you one unity probability for them. For the rest, I'll still give what is probably a generous 10%. Well, 10% multiplied by itself 15 times is 10 to the minus 15. There is only, 10 to the 11 stars in this galaxy. So the probability of seeing one Earth is 10 to the minus 4. Or you could say it another way. You should look through 10,000 Milky Way galaxies before you should expect to see one Earth. So that's a very sobering number. And really with this, I think I will close, that here's what we find. We find that which we would have intuitively said was obvious, that we look like we are in an exquisitely designed place, in a wonderful planet full of beauty and nurturing for life, turns out to be borne out when we observe other planets as well. And I would say we are still, someday, the way I spoke of the Drake 1961 equation, somebody will speak of my chart. And, 60 years from now, that will look really naive. But I think that the more the trend is, the farther we go, the more awestruck we are with the uniqueness of the Earth as a habitable planet. So I'll stop there and let you ask questions if you have any.